All right, hello everybody. It's Mr. Merrifield again. This week we'll be doing a review of scatter plots. So let's jump right in with some definitions. So a few things we're going to know: clusters, outliers, type of fit, and just strength going to be some key terms here. So we're just going to review those super quick, then we'll jump into an example. So it won't be a long video review this week because it's a concept that's pretty encompassing. We can scrunch it down into one example. So we'll try to go over some terminology, one example, then I'll post you guys some practice as well. So let's go over clusters. So we're just doing scatter plot. So if we have a set of data and we're trying to analyze it, so let's just go with like a basic scatter plot. We won't even define what our variables are. We'll just plot some variables, plot some points. So you might have something like this. And so our clusters basically just where data kind of congregates, where it all clusters together. So we could call that cluster number one, cluster number two. And we also want to describe things based on outliers. So outliers be our number two. We'll do another XY plot. And we might have something that follows like a nice trend. So not all data is going to be nice and clean, only if there's some kind of relationship should you expect that. So let's do something that's pretty nice and clustered, or excuse me, nice and strong. So if I drew a line through this, most of the data fits this trend right here. However, if you had a data point that was sticking out here, you would call that an outlier. Doesn't really fit the data set. And it gives you a hint that either something very strange is going on with this sample, or it could mean that an error happened in your recording. So next, let's go to type of fit. So of course, actually, let's just use that previous one. So of course, you can have a nice linear trend line. But as you'll kind of investigate, not everything follows that type of relationship. In fact, many things don't. So you might have something and you might have seen something like this in the news. You would call this kind of like a non-linear. So it follows a different type of trend. And of course, you could talk about the strength. So strength, we call it strong. Data fits the line very well. So let's do two examples, kind of the exact same trend line, but let's make one that's very strong, one that's very weak. So again, we'll maybe assume to pretty much roughly the same one. And you could have data that fits this extremely well. So you could have data that like all of these data points are almost exactly along this line. And you would call this a strong fit. Or you could have data that doesn't fit it very well. The trend line was made, however, it hardly fits that. You could have something wildly different, and you would call this a weak fit. Implying it's not a very good description of the data. So let's go into an example, how you apply this. So we're going to look at an example we looked at earlier in the year. This is our calories burned versus time spent exercising. So we don't really know much more about the situation other than this graph is telling us. So it's telling us that we've got some kind of data record with calories burned. That looks like it's the y variable. So let's define that. Y is number of calories burned. And let's see what else we can glean. So it also looks like they recorded it at random intervals. So or some kind of structured intervals, but not the same interval. So we've also got some data collected on X, the time in minutes. All right, so right off the bat, we can say, well, the more time I exercise, more calories I've burned. So we've got a positive fit. And I could try fitting quite a few different things on here, but you can see if I try to fit something that's non-linear, let's even try a different one. It doesn't quite fit very well. That looks pretty linear to me. So we got two things about it. It's positive, and it also looks pretty linear. So let's try to fit a line to it real quick. So all I'm trying to do here when I fit a line is I'm trying to make it as minimal amount of total distance from the points as possible. So to think of like the average distance between the lines and the points. So for instance, if I drew a line like this, not very good. These are very close. These are very far. So we're going to try to make it so all the points, the average distance is as small as possible. So I'll maybe start up here, try to kind of tweak it as best as possible. Maybe about there. So it doesn't have to be an exact. If you want to get very exact, you'd probably use a computer program to make this line for you after entering the data, but we're just going to do it by hand for now. So what I'm going to try to do with this trend line is I'm going to try to answer a question with it. So I want to try to predict something out. So I'm going to try to figure out how many calories are burned in 2 hours. So of course, 2 hours, not in this map. If we convert it, 60 times 2, we get 120, which is approximately out here. But my graph doesn't go up to 120. So I'm going to have to make an equation for this. So all I have to do, take my trend line, turn it into a linear equation. Again, I know the fit is linear, so therefore I can use a linear equation, and that will predict me anything. However, be careful with these, because you can kind of extrapolate out a little bit. But of course, if you extrapolate out too far, you're not going to get a good result. So, and you can even see if I try to predict like less than 5 minutes, so it would tell me I burn negative calories, which would say maybe don't use it to predict down here. But we're going to make our linear equation, see if that helps us find a solution to this question. So what I'm going to do first is I've got my y equals mx plus b. So I've almost got a checklist that I need to do. I need to find a slope term, and I need to find a y-intercept term, or a vertical shift. So y-intercept's probably the easier, but I'm going to have to estimate it. So if I go down here, that's about negative 100. I would estimate that my y-intercept is about at that point 0, negative 50. So got my y-intercept. Let's record that. B looks like it's going to be equal to negative 50. So got my y-intercept taken care of. Now let's take care of the slope. So what I'm going to do here is I'm going to try to find a point along here that's about as close to an intersection as possible. So maybe that one's pretty close, but not quite close enough. Let's see what the best one we can do here. Even if it hits on like a half hash mark, that would totally be fine. Let's maybe take, that looks about 30, 250. So I can use this and I can say, well, my run was 30. Now let's look at my rise. Well, it started here at negative 50 and it rose all the way up to 250. So that's about a rise of plus 300. So it ran 30, it rose 300, and we know my slope is just defined as my rise over my run. So I've got a slope here. It is just the ratio of 300 over 30. And that gives us a nice simple math that just reduces down to 10. 30 divided by 3, or 300 divided by 30, that's just 10. So I've got my slope, got my y-intercept, and that means we have our equation. So now I can write my actual, not just in generalized form, but my actual linear equation. That's going to be y equals 10x, and then plus a negative 50, but we can just write that as minus 50. So y equals 10x minus 50, which says that maybe we got a little warm-up period where we don't burn as many calories at the beginning, so this is kind of our fudge factor for that. And we burn about 10 calories per x, which is minutes, so 10 calories per minute. But we got a little startup time. You might not burn so many calories at the beginning, which is why we've got that intercept below. So now we're trying to answer the question, how many calories, which is our y, do we burn in 2 hours, our x? Well, that just means our prediction for this is 2 hours, so we set x is equal to 2 hours. And actually, I'm going to write that in a different color so it makes it a little bit more obvious what we're doing. So I'll write that in red. So we got x is equal, oops, there we go. X is equal to 2 hours. And our equation is just y equals 10x minus 50. So let's just plug that x in here. So the amount of calories I should have burned in 2 hours is y equals, oh, and one quick mistake here. Let's put this in the units that we use. So this shouldn't be 2 hours. This should be 120 minutes because we defined x as time in minutes. So be careful here. So that makes 10 times 120, not times 2, minus 50. So 10 times 120, that would just be 1200 minus 50. And we get our prediction, maybe not exactly what you'd have because you can see it does vary from the line a little bit, is 1150 calories, which if we just looked at our graph, we kind of predicted up here. 120 was where we said it'd come out to. Being a little bit over 1100 seems like a pretty good estimate. So in 2 hours, based on our sort of linear fit, creating an equation for it, plugging in our variable, we've got a prediction for 2 hours. It's approximately 1,150 calories. All right, so just a reminder, we'll have our office hours on Wednesday. I'll post some practice on this. So if you have any questions on this, please bring this to the office hours on Wednesday, and hope you all have a fantastic week.